Now let us discuss some special cases of Routh Hurwitz criteria, that how these cases can be taken care of. Now the first special case is that it sometimes the Routh table has 0 only in the first column of the row. That is in the first column of that some 0 is there, and second case is that it has entire row that consists of zeros. That entire row of 0 is there. So these are two special cases that we have to deal. Then we will discuss that how these special cases are dealt with. Now in the first case, if we have if the first element of the row is 0, let us suppose that this is 0 in that very case. So division by 0, by getting to get this value, we have to divide this by the term 0, that is this term. So that is division by 0 is required for the next row. Now to avoid that phenomena, so to avoid this divide by 0, an epsilon is inserted. That is, to avoid this, where 0 comes and epsilon is inserted or assigned to replace the 0 in the first column. Now then the value of this epsilon is allowed to approach 0 from either positive or the negative side, after which the signs of the entries of the first column can be determined. So instead of 0, we insert or we replace it with an epsilon. We can explain this with a small example. Now let us take the small example, that is of 0 in the first column. We have to determine the stability of the closed loop transfer function. This is the closed loop transfer function. We can form the Routh table, that is first starting by S5, then we have the S5, S4, S3, S2, S1 and S0. After that we can write, that is 1, 3 and 5, 1, 3 and 5 in the first column. Then we have 2, 3 and 2, 6 and 3 in the second column, 2, 6 and 3 in the second column. In the third column we find out, that is this into this, that is 6 minus 6 divided by 2, that is 0. Now one more point is taken into consideration, that when we are solving this, we first take the element of this second column, multiplied it with the second element, that is second row first column, minus this into this. That is whatever we do in this mathematics. It is inverse, it is opposite to that. That is, we first take this column multiplied by this column minus this into this column. Okay, I hope that you understand well. Now in this case we obtain 0. So divided by 0 is infinite. So instead of writing 0, we replace it with epsilon, that is this one. Okay, so then again we have we can do this, that is 6 epsilon, that is this into this, 6 epsilon minus 7 divided by epsilon, that is 6 epsilon minus 7, that is 2 into 7 by 2 divided by epsilon, and here we get 3. Similarly we get this equation here, and similarly we can do for all the rows, all the entries of the rows. Now we assume a certain sign for the epsilon, that is positive or the negative, and see that how the stability is affected by that. That is, in this case, let us suppose that here we have positive epsilon, we have considered as a positive value, and here we have considered as a negative value. Okay. Now from this, if this epsilon is considered as positive, from this table it is shown that a sign change from S3 to S2 row, that is, there is a sign change from S3 to S2 row, and another sign change from S2 to S1 row, that is, two sign changes are there, and the system is unstable as the two poles on the right half plane. Alternately, if we have considered epsilon as negative, in that very case we will see that there is a sign change from this to this, that is positive to negative, and that is S4 to S3 row, and another change from S3 to S2 row. Okay, and our result is exactly same as that for positive epsilon, that is positive and negative, the result is exactly same in both the cases, and the system is unstable, that is, we have the two poles on the right hand of the plane and the system is unstable in this case. Now another method which can be used if the 0 appears only in the first column, that is, if we have the 0 in the first column, and one more method is used in that very case, that is reverse coefficients. That method is known as the reverse coefficient method, when it can be used when there is a 0 only in the first column. Now it is derived from the fact that the polynomial that has the reciprocal roots of original polynomial has the roots distributed the same right half plane, left half plane, and imaginary axis, because taking the reciprocal of the root does not move it to the another region. Thus, if we can find the polynomial that has the reciprocal roots of the original polynomial, then in that very case it is possible that the Routh table for a new polynomial will not have a 0 in the first column. That is what we can do. If we can find a polynomial that is the reciprocal of the original polynomial, then definitely it doesn't have the 0 in the first column, and this method is usually computationally easier than the epsilon method that we have described here. Now we now show that the polynomial we are looking for, the one with the reciprocal roots, is simply the original polynomials with coefficients written in the reverse order. So it is already shown by this Phillips in 1991, that is, it is shown by Phillips in 1991, that is polynomial, the one with the reciprocal roots is simply the original polynomial with its coefficient written in the reverse order. Now let us assume an equation. That is Sn plus an minus 1 Sn minus 1 plus a1s plus a dot equals to 0. Now in this case, let us suppose that this is replaced by S is replaced by 1 by D. Now when we substitute this equation, we finally get this equation, and factorizing out 1 by dn, finally we are getting this equation, and final equation is this, Okay, and so from this we can see that the polynomial with the reciprocal roots is the polynomial with the coefficient written in the reverse order. That is, in this case the polynomials are written in the reverse order. Now let us redo the previous example to show that how we can get another computationally efficient method for that. Now we have to determine the stability of the closed loop transfer function, that is the previous example. In this case whatever we get from the discussion, that this polynomial that is we write a polynomial that has the reciprocal roots of the denominator, and this polynomial is formed by writing in reverse order, that is 3s5, then we have the 5s4, 6s3, 3s2, 2s and 1. That is, we have to write this equation in the reverse order, and after that we form the Routh table. We form the Routh table from that, and from this we will see that there are two sign changes, that is S2 to S1, then S1 to S0. There are two sign changes. The system is unstable in this case, that is, we have the two right half plane poles, and so, and also we can observe that there is no zero column in that, and there is no need to insert the epsilon in that. So in this way the calculation is easy in this method. Now we discuss the second special case. Sometimes while making a Routh table, we find that the entire row consists of 0 because there is an even polynomial that is a factor of the original polynomial, which makes the entire row 0. This case must be handled differently from the case of 0 in only the first column of the row. Now let us look at the example that demonstrates how to construct and interpret the Routh table when an entire row of 0 is present. Now let us consider it. This is a problem. We have to determine the number of right half poles in the closed loop transfer function. Let us consider this closed loop transfer function, and we have to form the Routh table. And now in this case the Routh table is formed like that. Here we have 7, 42, 56. We multiply it by 1 by 7, and we are getting 1, 6 and 8. Again we get here 0, 0 and the 0. So the whole of the row becomes 0 in this case. Now we stop at that particular row, that is, since whole of the row is 0, so we stop at this particular third row. Since the entire row consists of zeros, and we use the following procedure after that. First, what we do, we return to the row immediately above that row. That is, we return to the row immediately that is above that row, that is the second row. That is, we return to the row immediately above the row of zeros and form the auxiliary polynomial using the entries in that row as the coefficient. That is, we make the auxiliary polynomial by the entries of the row above the 0 row. The polynomial will start with the power. The polynomial will start with the power of s in the label column and continue by skipping every other power of s. Now in this case the polynomial formed would be, that is, s4 from this one, then we have 6s square from this one, and then we have 8. So this polynomial formed is s4, 6s square plus 8, and then we differentiate that polynomial with respect to s we differentiate this polynomial with respect to s, we get 4s cube plus 12s plus 0. Finally, we use the coefficients of this equation. We use the coefficient of this equation to replace the row of zeros. Okay, so we replace 0 by 4 from here, then we replace 0 by 12 to here. Again, since these it has a common factor, we multiply it by 1 by 4, and finally we are getting 1 and 3, and here it is 0 again. So the table is formed in this straightforward manner, that what we do, we find the rows of row in which 0 is there, then we go to the previous row and find the auxiliary equation, and then differentiate that equation, and by differentiating, we whatever coefficient we are getting, we substitute in that equation where there is 0. So this is a simple way to do that. Now let us look further into the case that yields the entire row of zeros. The entire row of zeros will appear in the Routh table when a purely even or purely odd polynomial is the factor of the original polynomial. That is, purely even and purely odd polynomial is the factor of the original polynomial. Here we see that this one is the even polynomial. It only even powers of s in this case. Now the even polynomials have roots that are symmetrical about the origin, and this symmetry can occur under the three conditions of the root position. That is, the roots are symmetrical and real, the roots are symmetrical and imaginary, and roots are quadrantal. That is, roots under these three, the symmetry can occur under these three conditions, that is, roots are symmetrical and real, the roots are symmetrical and imaginary, and roots are quadrantal. So the example of these three cases is shown in this figure. In this case, if the roots are real and symmetric, then we get the roots here, that is, these are real and symmetrical about the origin, imaginary and symmetrical about the origin, that is B, this one, and quadrantal and symmetrical about the origin, that is C. Okay. Now it is this even polynomial that causes the row of zeros to appear. That is, row of 0 is due to the even polynomial, which is the factor of the original polynomial. Thus the row of 0 tells us the existence of even polynomial whose roots are symmetric about the origin. So this row of 0, what this row of 0? This row of 0 tells us the existence of even polynomial. That is, if we have the row of 0, it means that there is the existence of the even polynomial whose roots are symmetric about the origin. Some of these roots can be on the j omega axis. On the other hand, since jw roots, that is j omega roots, are symmetric about the origin, if we do not have the row of zeros, we cannot have the j omega roots. Okay, that is, this 0 row tells us about the existence of the even polynomial is there, and whose roots are actually the symmetric about the origin, and some of these roots are on this j omega axis, and since j omega axis are symmetric about the origin, and if we do not have the rows of zeros, then we cannot possibly say that it has j omega roots. Now other characteristic of the Routh table for this case is that row previous to the row of 0 contains the even polynomial that is a factor of the original polynomial. That is, whatever we have done, we have this 0 row and the previous row of the 0 row is actually the even polynomial that is the factor of the original polynomial, and finally everything from the row containing the even polynomial down to the end of the Routh table is the test of that even polynomial only. Now with this example we can discuss that how this case can be taken care of. Now let us take a transfer function, and we have to tell that how many poles are on the right half plane, on the left half plane, and on the j omega axis. We find the Routh table. From this we find that this S3 is the 0 row. As we have discussed already that the 0 row, the above the 0 row is the even polynomial of that function. So even polynomial can be extracted from this one, from this S4 row, that is 1 into S4, 3 into S square plus 2. Okay, and we then differentiate it. And we take the derivative with respect to S to obtain the coefficient that replace the row of zeros in this. That is, we replace the row of zeros, so we differentiate it. Okay, now we interpret this Routh table. That is, we replace this 4 6 in this S3 column, that is, we replace it 4 and then 6, and then we multiply it by 1 by 2. We get this equation. Now we have to interpret it. Since all the entries from the even polynomial at the S4 row, that is all the entries from this S4 row to S0 row are the test of the even polynomial, we begin to draw some conclusion about the roots of the even polynomial. That is, no sign change exists from this S4 to S0. There is no sign changes there. Okay, so even polynomial does not have the right half plane poles. Since there are no right half plane poles, so no left hand plane poles are there because of the requirement of the symmetry in this case. Okay, hence the even polynomial must have all the 4 of its poles on the j omega axis. Okay, again, that is, we can discuss again, since this from the S4 to S0, it is a test of even polynomial, and also no sign change is there in the polynomial, so there is no poles on the right half plane, no poles on the left half plane. Since we must have the 4 roots, that is S4 in this case, so all the poles, 4 poles are on the j omega axis. Okay, now that is we have the poles on the j omega axis, that is from S4 to S0, which is a test of the even polynomial. Now remaining roots of a polynomial are evaluated from S8 to S4 row. This was for the even polynomial, and remaining roots are evaluated from S8 row down to S4 row. And in this case we see that there are 2 sign changes in the first column. Thus the other polynomial have 2 roots on the right hand plane, that is 2 roots on the right hand plane due to the this changes, okay, and the because of the symmetry 2 on the left half plane, because total we have to take care of 4 roots. So for the fourth order we have the 4 that is poles on the j omega axis, then other 4 we have the 2 on the left hand side, 2 on the right hand side, then the total 8th order we have 2 on the left hand side, 2 on the right hand side, and 4 are on the j omega axis, okay. And since from this we conclude that it is the unstable system. So from this we conclude that we have learned about the the polynomials that generate entire rows of zeros in the Routh table. These polynomials has purely even factor with the roots that are symmetrical about the origin. The even polynomial appears in the Routh table in the row directly above the rows of 0. Every entry in the table from the even polynomial row to the end of the chart applies to the even polynomial. Therefore, the number of sign changes from the even polynomial to the end of the table, from this even polynomial to the end of the table, equals to the number of right half plane roots of the even polynomial. Because of the symmetry of the roots about the origin, the even polynomial must have the same number of left half plane roots as it does right half plane roots. Having accounted for the roots on the right hand and the left half plane, we know that remaining roots would be on the this j omega axis, okay. Every row in the Routh table from the beginning of the chart to the row containing the even polynomial applies only to the other factor of the original polynomial. That is, the row from the beginning of the chart to the row containing this even polynomial applies to the other factor of the original polynomial. For this factor, the number of sign changes from the beginning of the table down to the even polynomial equals to the right half roots, and the remaining roots are the left half plane roots. That is, from this even polynomial to down, we also have to see number of poles on the j omega axis. However, from the top to the even poles, only right and the left half roots are there, and there are no j omega roots contained in this other polynomial. So no j omega roots are contained in this case. Now you have to do this example at your own end. That is, we have used the Routh Hurwitz criteria to find out how many poles of the closed loop transfer function are on the right hand, left hand, or on the j omega axis. So for your convenience, this is also given, answer is also given, so you have to do at your own end. So this is how that we have to deal with the special cases. We have dealt with the 2 special cases. In the first special case, the row of the 0 was there, that how that is the row of the 0 would be there, that it can be taken care by epsilon method, and then it can be taken by this inverse method also. We have discussed this, that is by epsilon method or by the reverse coefficients. And second, when the entire row is 0, that how the previous row is the root even, how we have created that even root, and then we draw the conclusion out of that. So this is how all the cases are covered in this case. In the next lecture we can discuss some of the examples about this only, and then how we have to do the stability design by the Routh criteria. Thank you very much for this now.